Good afternoon to all. This is Professor Yulikar. We are here to study the dynamics of machinery test week. So this is your vibration test week. So in this test week there are 4 to 5 practicals are conducted, and in this out of these 4 to 5 we are going to discuss about one of the practical setup. That is, aim of this setup is to find out the natural frequency of single degree of freedom system subjected to torsional vibration. Okay. So if you observe here, you will come to know here one comparatively longer shaft which is fixed at one end, and its other end a flywheel is connected over which the drum is mounted. Okay, and there is a provision for putting the paper to draw the amplitude of this generated vibrations. Okay, and here one damper is there, and here a provision is provided to put the pen over here. So like a stylus experiment, a stylus instrument, we are going to plot the generated vibration response of this system on this paper. Okay, so now as far as experimental procedure is concerned, what we are going to do, we are conducting this experiment with 2 cases. In its first case, we are considering full damping. Now we are familiar with the concept of damping. Damping is nothing but the resistance provided to the motion. Okay, and in another case we are going to conduct this experiment without damping. That is, only air damping is there, which we are neglecting. Okay, now first, if you observe, you will come to know here in this drum the viscous oil is there. Grade of this oil is SAE 40. Okay, multigrading oil is there, and we are providing damping with the help of that oil. Okay, now as far as procedure is concerned, what we are doing, we are providing torsional vibration to the system. Now what exactly the torsional vibration? The vibrations in which each and every particle of the body is moving approximately circular to the axis of the shaft. Okay, now as far as procedure is concerned, we are going to what we are going to do, we are just providing this system torsional vibration. Okay, and number of oscillations upon time we are going to record. That gives us experimental natural frequency. Okay, now in second term here, if you observe, you will come to know this stylus I am putting this initially at its top position. Okay, and when I am providing the torsional vibration, this viscous damper, the pen is moving in a downward direction with constant velocity, which plots the graph of this kind. Okay, now with the help of this graph we are finding out the amplitude with damping and without damping. Okay, now in second case the same experimental procedure is there. What we are doing, we are draining this oil from this drain, and we are repeating the procedure. Okay, again I am providing torsional vibration. Again this pen is at the top position, it will move in a downward direction with constant velocity. Again it will plot a graph. Okay, so that we will get 2 plots. Okay, and for each case we are going to record 3 cases. Okay, means 3 iterations, and out of these 3 iterations we will get 3 graphs, and we will measure the respective amplitude, and its calculation can be shown to you in its calculation part. Okay, here we are going to discuss the calculation part of this same setup to study the torsional damped free vibration. Okay, subjected to single degree of freedom system. Here we are going to consider first part, that is full oil, that is with damping condition. Okay, so here first we find out the theoretical calculations, and then we are going to discuss about the experimental procedure, experimental calculations. Okay, so here first step is to find out the mass of the disc. Formula is rho into G into H. Polar moment of inertia can be calculated. As we all know, polar moment of inertia is the moment of inertia of Ixx and Iy. Okay, and formula becomes pi by 32 d raised to 4, where d is what? D is the diameter of the shaft. Okay, now third step is to find out the mass moment of inertia for the disc as well as drum. Okay, for disc I will use the formula mr square by 2. For drum I will use md into rd square. So final formula becomes mr square by 2 plus md into rd square. Next step is to find out the torsional stiffness, which can be find out by using the torsional equation, and final output becomes G into J by L, where G is the torsional modulus of rigidity, J is the polar moment of inertia, where L is the length of this entire shaft. Okay, then natural frequency can be calculated by using basic formula which we have seen several times, omega n equal to root of kt by I, where this kt is known as torsional stiffness and I is mass moment of inertia. Time period, basic formula 2 pi upon omega n. Frequency is inverse, as we all know, inverse of time period. Critical damping coefficient is Cc, in the torsional case we use Cct, okay. So it becomes 2 into root of Kt into I. Then we also find out the logarithmic decrement, okay. Logarithmic decrement is what? Natural log of amplitude of vibration on the same side of mean position, that is ln of x2 upon x1, okay. Then last part is damping factor, that is zeta. Using, when we have the logarithmic decrement, we use this formula, zeta equal to delta upon root of 4 pi square plus delta square. Then damping factor is known as Ct upon Cct, the damping coefficient, theoretical damping coefficient. Then we will see, once we will have zeta, we can calculate the damped natural frequency omega d equal to omega n into root of 1 minus zeta square. And finally, damped frequency becomes omega d upon 2 pi. Okay, so this is how we can calculate the FD using theoretical procedure, and experimentally, as I already told you, number of oscillations we have recorded as well with respect to time. So number of oscillations upon time, that gives me experimental natural frequency, that is, and damped time period can be calculated by inversing this value, that is 1 upon FD equal to time period record for this damped natural frequency. Okay. So this is how we are going to calculate the damping coefficient as well as experimental procedure and theoretical procedure to find out the natural frequency of single degree of freedom system subjected to torsional vibration.